two, or hello. In this video, I wish to introduce some of my ideas and philosophies about teaching differential equations in particular, and I think a lot of these ideas pass over to a lot of other types of mathematics, but differential equations is what I have the most experience with and the most have been the most productive in developing resources to support my teaching there. So that's what I'll focus on today. And I think that students need to be able to experience the mathematics, to experience the differential equations and see the consequences and the ramifications of decisions that they make and choices that they make, to see how they can learn from that and use that to guide um, their work when they come to work problems on their own. I'll talk about a couple of different things here today, but the big overlying themes, I think, are that they're going to be able to somehow visualize, experience the mathematics graphically and or algebraically. So here is our first example. We see this colorful grid here with a number of different things, and I see in the left-hand column I have my parameters for the differential equation, the coefficients a, b, c, and then the right-hand side f of t. The differential equation is displayed here in the top row in the middle. Below that, I see the fundamental set of solutions, y1 for the homogeneous problem, y1 and y2. And then the last row here is a particular solution. And I see that for this problem, the characteristic equation has roots -2 and -4. So my fundamental set of solutions is e to the -4t and e to the -2t. And then a particular solution with the right-hand side of t e to the -2t works out to be minus a quarter t plus a quarter t squared, all times e to the -2t. So this linear function times e to the -2t gives me a quadratic t squared and t e to the -2t. If I change the problem a little bit here and add a lower order term to this, so I change the right hand side. If I change from t to t plus 1, right, and then update the problem, right, then I see that the coefficients change, but I still have the linear and quadratic times e to the -2t. And again, I get the increased power of t there because I would not guess the solution in homogeneous solution. So I get one higher degree there. If I change the differential equation, if I change that 6 to a -6 and update the solutions, ooh, I don't know if I like that so much. My problem was updated. My homogeneous solutions were updated. My particular solution doesn't look so good. And this gives me an opportunity now to see exactly how this resource has been implemented. And so what I have here in a Maple worksheet is I have a table, and I've done different colors to indicate things, but you can see the rows and columns, and over here there's a couple cells that have been merged together. And if I look at each one of these, if I right click on one of these cells, I see that these are all embedded components, and that component property is a text area, and I gave it the name TAA. The names are case sensitive, and I can set the width of it, the number of rows, colors. I can set different values for this. I can protect things. I can make them visible or editable, and I'm not going to change anything there. The last one here is not a text area, but a math container, because I have a little bit more math and a little bit more nodes, a little bit longer, so that works out a little bit better there for the wrapping and everything. So again, you can set different parameters of that, okay, and those are just kind of containers to have information. These columns down here in the middle are, again, these are going to be math containers that have math results that are going to show up in them. And this is a relatively simple resource here. All the action takes place in this bright green Update Solutions button. And this is a button, right? And so on that button, there's an action that goes along with, we set the properties of this button. And then with this button, right, we see that when this button is clicked, what's executed is this command update all. Now, update all is a procedure that I have defined in the startup code. Right, so I need to close this, and now I can come up here and I can look at the startup code. Right, and so this has some Maple commands in it. It's not all that long or complicated here. We start by clearing the Maple memory. We load the document tools package, which has a number of resources for working with embedded components. Primary ones are get property and set property that get and set and put the values in an embedded component. Here so this update all procedure starts by getting the current values of A, B, and C, and F. We get those from the text areas in the math container. We then put them together to form the differential equation, and then I write that differential equation into this field, math container DE. All right. Then I look at the corresponding homogeneous differential equation. I solve that, and I get I construct the two homogeneous solutions, right, y1 and y2, and then I also then get the solution of the non-homogeneous problem where I set C1 and C2 equal to 0 to get a particular solution, and then I output these results to the relevant containers, the y1, y2, and yp containers. So that's all this resource does. When I click this button, it reads the values of A, B, C, and F, displays the different non-homogeneous differential equation, homogeneous solution, and then the particular solution. And the whole point of doing this was I didn't really like the way this solution looks. And so what I needed to do here is I need to simplify. I'm just going to modify this code to simplify that result before I display it. Okay, and I'm going to save this code. And then I need to re-execute the worksheet, re-execute the startup code region to redefine what happens when I push that button. And so where are my exclamation points? There they are. Re-execute the worksheet. And now if I push update solutions, yes. So now this solution is simplified before it's displayed. And so now I see that when my homogeneous solution does not include e to the minus 2t, my particular solution is just of the same form, the linear function times e to the minus 2t. Right, and so students can, right, for the second problem I want to look at, I want a little more complicated, a little more interactive, a little more specific here. And so this is the method, practice applying the method of judicious guessing. And here it is in the browser, and I can also download it to my right. So again, we see that there's a startup code region where everything is defined, and we want to say yes. You see some of the same gaudy colors that I had in the previous one. You still see this general table layout. There's a little more to it here. Again, we have A, B, C, and F as before, an update problem in a new place, the differential equation, the fundamental set of the homogeneous problem. But now the question is, we want to guess the right form for the particular solution, and then we're going to see if that worked or not. So, all right, so here we have our problem, and if I have right, a homogeneous solution has e to the 2t and e to the 3t in it, then the sine and cosine, the cosine term, cosine 2t, is going to need two terms, a times cosine 2t and b times sine of 2t. The e to the t term is not in a homogeneous, so a constant times e to the t will work. Then I have a constant, which will work by itself. I left out d because d has its own meaning in Maple. And then I have the t squared e to the 3t. So t squared e to the 3t is going to suggest a quadratic, ft squared plus gt plus h times e to the 3t. But since the h e to the 3t is in a homogeneous solution, I need to multiply that guess by t. So if I take this guess and plug it into the non-homogeneous differential equation, I get this result. Right, here is this y, capital Y of t double prime minus 5 times the derivative plus 6 times capital Y. That's all of this on the left-hand side here, and that's supposed to be equal to the right-hand side, my function f. And in order for that to happen, you have to match up each of the coefficients. So cosine of 2t, so 1 needs to be 2a minus 10b. E to the t's coefficient is 1, needs to be 2c, so I can see right away then that c is going to be a half. 3, a constant term, has to match up with 6e, so e is also going to be a half. And the t squared e to the 3t matches up here, t squared, the 3f, t squared e to the 3t, right? So 3f is going to be 1, then 6f plus 2g is going to be 0, and 2g plus h is going to be 0, and I think that's all, and the sine term is also going to be 0. That gives me all the equations. I think it's going to be, what, 7 different equations for the 7 different unknowns. 1, 2, 3, 4, 5, 6, 7. Right? and so I plugged it in. I can match the terms, and so there are the equating all the coefficients. There are the 7 equations that need to be satisfied. This is pretty easy to go through and solve most of it, but we can also ask Maple to do that. We get a solution, and then we can plug those constants into my guess to find a particular solution. And that all worked fine. Now, what would happen, right, from the student point of view, what happens if I forget to multiply this guess by t? If I forget to recognize that h e to the 3t is in a homogeneous solution, so it can't be part of my particular solution. If I plug that into the differential equation, then all the other lower things have disappeared, and I get this new expression. And if I try to match up the terms, here's what I get. It's an equation, of course, and if I solve that, it's going to tell me it's inconsistent. And so there's no particular solution of this form. My guess, this is what happens if your guess is not right. Right, you get an inconsistent system of equations that has no solution, and you don't get a solution. The coding of this is very similar. These are all text regions. This button here, this update button, right, that calls it update the problem, right? So that's just going to update the information up here. These other buttons down here, right, those are going to have other procedures that they call plug in, match terms, solve coefficient, and find particular solution. And instead of putting all the details of those codes in each one of those boxes, I prefer to put all that in the startup code region. Okay, and now we can see that. And now this one's a little bit longer than what I had before, but it consists of just a number of procedures. The update problem looks a lot like what I had before, where I get information from, well, I get information from the problem, and then I write the differential equation out. And I write the homogeneous solution out. Now the other buttons here, right, I'm changing the action, the availability of other buttons. Right, so the first thing I do is I turn off all of the other buttons. The plug-in button, the match button, the solve coefficient, the particular solution, the plug-in. All right, so I make them all disabled, and I also empty out any old results that were there. So I set them to contain empty results. All right, and then I update the problem, and I put the problem in the homogeneous solution, and then when I'm done with that, I turn on the plug-in button. In the plug-in procedure, right, again, I clear out some parts that are relevant there. I get the information I need, and then I do the operation. I plug in and simplify and collect everything to get the expressions that I get, that I would get for this problem, and then set up the buttons for the next step. Match terms. I go through this process. This was difficult, and I had some help from the people at Maple to actually make this work. Put the code in the middle here, but again, I get information that I need from the GUI. I do the computations. I write the results out, and I turn on the next buttons. Solving the coefficient is similar. Third resource I want to look at, right? So this one, the new thing here is that we have a slider. And a slider is, again, another kind of Maple element, right? And so the component properties here for the slider, we have a name for it. We can set the limits, the range of values, the default value of the slider, tick marks, widths, height, colors. We can set some other properties for how the slider works. So here, in particular, I've clicked the continuous update on drag. So as I drag the slider, it's going to show me the results along the way, not just when I stop and drop it. And the action here is what happens when I slide the slider. I'm changing the frequency of the forcing function. I see the effect in the solution. I also see the effect in the general solution. And if I click on, right, so as that slider changes, right, what I do is I get the value from the slider, put it in a global variable, omega. I set the property in, this is going to be the omega value up here, right? Text area omega. So I set the value of text area omega to be that, and I update the user interface, which is updating the graph and updating the solutions. And so as I slide this slider around, everything changes. And what I want to see here then, so you see the phenomenon of beats happening, and you also then see what happens when I get, well, here I'm very close to hitting that. If I make this exactly, I can also change this to make this 2, right? And I see there resonance occurring. I have other things for other topics related to differential equations, but I think these illustrate some of the basic ideas of what I try to do in my class. And I welcome any comments, criticism, suggestions, other discussion. I'm happy to engage in any of that. So thanks for your time, and